Yes. Okay.
Okay, I think we should get started. So Kazushi Kinoda is going to give us part 2 of his lecture on experimental studies of spin liquids.
Yeah. Okay, let's resume the issue of the spin liquid. Okay, yesterday in my yesterday's lectures, I showed you some experiments which evidences the quantum spin liquid nature and magnetic ordering depending on the degree of the frustration of the lattice. And the materials, two materials I showed. One is the deformable triangular lattice, and the other one is the nearly isotropic triangular lattice. And the deformable triangular lattice shows the clear magnetic ordering below 25 or 26 kelvins, which is clearly indicated by the splitting of the NML line, as I showed you yesterday. And however, the nearly triangular lattice does not show any clear splitting or for the change of NML spectra at low temperatures. So this is the unambiguous evidence of the non-magnetic ordering, and very probably indication of the spin liquid. And in conventional many-body systems, the interaction between the among the ingredient leads to some kind of order. In spin systems, usually the ferromagnetic or anti-ferromagnetic or ferromagnetic or spiral, or anyway, some ordering state results, and which is regarded as some classical order. And the excitation from the ground state is described by some particles in spin systems, the magnon. But in spin liquid systems, interaction is there, and the very strong interaction works between the spins. However, in the absence of ordering, so what is the excitations? How the spin excitations occur? To look into the nature of the spin excitations, the thermodynamic measurements is a very, very powerful probe to know the excitations. So these are specific heat results is one of the most striking results in spin liquid material. And left-hand side shows the C over T, the specific heat divided by temperature as a function of T square. This is the conventional plot of the specific heat of the metal. And usually this intersection gives the coefficient of electronic contribution to the specific heat, gamma term. Maybe you know the C. Whoa. Okay. Yeah. Okay. This is needless to say. Maybe C equal gamma T plus beta T square. The electronic contribution, lattice contribution, C over T is gamma plus beta T square. Sorry, yeah. So this gamma is in metallic state is proportional to the density states. So textbook says that the insulating materials, the gamma term, namely intersection, should vanish. And the data plotted in this figure is for insulators. All of the materials are insulators. And anti-ferromagnetic Mott insulators shows vanishing gamma as expected. However, the spin liquid materials, is insulator, seems to show a finite gamma. And this group, Osaka University group, extended the measurements down to lower and lower temperatures, millikelvin range, and they confirmed that the gamma is finite, roughly. Okay, I can show the exact values of the gamma. Next paragraph. Anyway, finite gamma. And they also found that some anomaly in specific heat around 5 Kelvin or 6 Kelvin. This is a T square. Maybe T equal 6 or 7 Kelvin. Some anomaly occurs. But at present, I do not into the details of this feature. Okay, please take a look at this one. Yes?
So in the left figure, there are 3 other materials that shows TQ.
Yeah, these are TQ behaviors.
Is the three-dimensional?
And three-dimensional, always material is three-dimensional. So the ordering is three-dimensional. But maybe for these questions, the temperature dependence of the specific heat maybe asks answer, because in the two-dimensional systems, the spin wave is a T square, but in real materials, there is a magnetic anisotropy. In that case, always the activated. So I think that the magnetic ordering occurs in these materials 20 Kelvin or 30 Kelvins. So in these temperature regions, all of the magnetic excitation dies out. So this temperature dependence is solely comes from the difference of the phonons, we think. No spin waves. Yeah. Yes. Yeah. Due to the anisotropy of the no spin gaps, it's activated behaviors in the system. Okay. This is a comparison of the spin susceptibility and then specific heat gamma. The gamma is 13 millijoule, and the low temperature limit of the spin susceptibility is roughly 3, 10 to the 4th. Okay, the Wilson ratio characterizes the degree of the film liquid. For example, this in free electron gas, the chi is divided is expressed as this. This is the Pauli susceptibilities, and this is the free electron gamma values. Yeah. So RW Wilson ratio should be unity 1 m non-interacting electrons. But in usual correlated electrons, this susceptibilities is generally enhanced somewhat than the expected susceptibility from the gamma value. So in real materials, RW Wilson ratio is 1 or 2 or no 3 or 1 or 2. So this means this spin liquid insulator looks like metal, because the Wilson ratio is 1.6. It's very conventional values for film liquid values, but this is the insulator. Okay. So this is very striking results, because despite of the insulating states, it seems that there is some fermionic stuffs are there in these materials. So they are the Osaka University groups extended the measurements down to the very low temperatures, and this is the linear temperature dependence, and then finite intersection appears. But at the lowest temperatures, they encountered the abrupt enhancement of the specific heat. This is due to the nuclear Schottky relaxation, Schottky contributions, because these materials contains copper ions. Copper is non-magnetic and closed shell, so no vital low in the electronic properties. However, copper spins is 3 or halves. So this is this spins when these spins reside in the field gradient situations. It's a two-level. These spins forms a two-level systems. So this is the Schottky. These couple spins, nuclear spins, shows the Schottky contributions. So this is the tail of the Schottky contributions. However, except this lowest temperature region, the behavior seems like linear, and then this interception gives the gamma value of 13 or 14 millijoule. This value is not so large, but it's not so small. This is a very conventional values for metal in organic materials. So these values cannot distinguish between the insulators and metal as far as the magnitude is concerned. And however, thermal conductivity measurements gives the contradictory data, somewhat contradictory data. They measured the Kyoto University group measured the thermal conductivity down to 30 or 40, no, 10 millijoule, 10 millikelvin also. No. Several 10 millikelvin, yeah. And they observed a couple over T plotted as a T squares. This plot is equivalence of the this plot and specific heat. And what they found is this the tendency of the data as toward the zero vanishing values and couple of T. And this is suggestive of the finite excitation gap. And from this data, they deduced, they obtained that the gap is 0.4 or 0.5 Kelvin. Anyway, this is very, very small because the exchange interaction is 250 Kelvin in this material. So this gap is 3 orders of magnitude smaller. So even now, this contradiction between the specific heat data and thermal conductivity data don't find agreement. But anyway, what at present what we can say is this material is gapless or marginally gapped. So this is tiny gap, if any. Yes.
So how do you understand field dependence?
Field dependence, and this specific heat does not show any field dependence up to 8 Tesla. So, and they maybe reported some field dependence at higher temperatures. So they speculated some about some contribution from the Bison or something like this, but I'm not sure. At high temperatures, this is the sample dependence. No, sorry. You're asking this field dependence? I don't know. Yes, the data at 0 Tesla, and then this, couple is enhanced, but a little bit enhanced there. But I don't know. But from in specific heat, there is no field dependence. So, in this, even in this respect, is no agreement. But I have to say that this is a specific heat is a purely thermodynamic quantity, and thermal conductivity is thermodynamic in some sense, but in other sense, it's a transport. So under the magnetic field, how to thermal energy transport is depending on the samples, the disorder. Depends on the degree of the disorder or something like this. So its thermal conductivity is very sensitive to such a kind of the sample situation. But I'm not sure. But anyway, this is the some sort of the transport measurement. So, but anyway, this contradiction. But from theoretical point of view, this experimental data, the finite gamma is very clear, has a clear consequence that the some fermionic, independent fermionic stuffs are there. But from the theoretical point of view, U1 spin liquid, the theoretical predictions is the C over T should be proportional to this curious power law, and kappa over T is also curious power law. So this means that the even this strange and then the data suggestively fermionic stuffs, this is still it's inconsistent with this U1 gauge, U1 spin liquid. So some other spin liquid may be possible. And one possibility is the Anderson localization of spinons. But I'm not sure. Anyway, the many contradiction. One is between specific heat and thermal conductivity, and the other one is between experiments and the theory. So completely open questions. So this is the problem which you should challenge. Okay, I'd like to show you the relevant related results in analogous materials. And this is the different these materials consisting of different molecules of palladium DMIT2. You can forget about this the details of molecules. Anyway, this palladium DMIT2 is a one molecule like this. It's a planar molecule like the BEDTTTF, abbreviated to ET, as I talked so far. So these are layered structures. This palladium DMIT2 forms a one monolayer, and A is insulating layers, and there's a cation. Many kinds of the cationic molecular species residing in the insulating layers. So the layered structures like the BDTTF materials and insulating, conducting. But this materials is a Mott insulator, so the whole system behaves like an insulator. And this is the in-plane structure of the molecule. And this palladium DMIT2 molecule forms a strong dimer, like the materials I talked yesterday. This strong dimer forms a two-dimensional network, and the transfer integrals roughly characterize the transfer integrals. Two kinds of transfer integrals are there: T prime and T. So anisotropic triangular lattice. And the very good points of these materials is that the materials has a very finely tuned parameters for the anisotropies. So this methyl phosphorus, methyl arsenide, and many cationic molecules are there. And this anisotropy, T prime over T, is controlled by this species, molecular species. And if this cation reside in these insulating layers, the T prime over T is 0.6 something, less frustrations. Frustration is weak. And you can change the cationic species from here and here. And this material is ethylene methyl 3 antimony. This molecule residing this insulating layers, and this materials shows a spin liquid behavior. So the Néel order, this is the Néel temperature. Néel temperature and the degree of frustration has a very clear correlations. As the frustration is stronger, the Néel temperatures is suppressed, and then spin liquid occurs. in these regions. So the thermal conductivity and the specific heat measurements shows very consistent results as far as these materials is concerned. The left side figure shows the specific heat. This is the charge ordered insulators, which shows the vanishingly small gamma as expected. But this is spin liquid material. Has the finite intersection. And the right-hand side figure shows the thermal conductivity divided by temperatures. This is also this non-spin liquid materials shows the vanishing capability, but the spin liquid materials has finite values at 0 temperatures. So for these materials, the specific heat measurements and then thermal conductivity measurements are happy to each other. And so the people believe that in these materials is a gapless spin liquid. There is no experimental data showing the finite gap in these materials. And interestingly, we can compare the specific heat gamma and then spin susceptibility at low temperature limit here. So you can calculate Wilson ratio, and the Wilson ratio is 1.6, nearly exactly the same value of the previous spin liquid materials. So two spin liquid materials shows nearly exactly the same Wilson ratio. So we think that the two materials carry the similar kind of spin liquid, I think. Okay, there are several mysterious results, but here I'd like to show you one key results which is still open questions. Gives the open questions. That is the anomaly that occurs at 6 Kelvin. We call this 6 Kelvin anomaly. And around 6 Kelvin or 5 Kelvin, 7 Kelvin, in this temperature range, various anomalies occurs in various quantities. And for example, specific heat is a broad hump occurs, and thermal conductivity shows some kink. This temperature range. This is different sample, so sample dependent. However, the magnitude is different, but around 6 Kelvin, some kink occurs for both samples. And animal relaxation rate shows a steep decrease around these temperatures. And this is the thermal expansivity, which is also thermodynamic quantities. This shows some anomalies around 6 Kelvin. And this anomaly seems very sharp. However, in thermal expansion coefficient, if the transition is of the second order, in that case, a very sharp peak. So they say this is very, very broad, the signature of the very broad transitions. And this nature of the transition is broad in other materials. You can see this NMR anomaly is not a clear anomaly, it's some crossover here to here. And also ultrasonic velocity shows some softening of the lattice around 6 Kelvin. So something happens around 6 Kelvins. And the origin of this anomaly is completely open. But some theoretical suggestions may be relevant to these anomalies. Among them, the instability of the spin-on-film surface is one conceivable candidate. As I explained yesterday, the degenerate system with filmy surface is unstable because the degeneracy is inherently very weak against any perturbations. So if the spin-on film surface is formed, this spin-on film surface is likely or may be destroyed by some other perturbation or interaction between the constituent particles. So several the Fermi surface, spin on Fermi surface instabilities is suggested, and one like a superconductivity. It's so please compare the two results. And this is a spin liquid material, and this is the superconducting material, and 10 Kelvin superconductor. Can you distinguish between the two data? It's very similar. And please take a look at this thermal conductivity. This is a spin liquid material, some Kinko cores, and some Kinko cores, and this is the spin liquid. This is a superconductor. This is a spin liquid insulator. So, apart from the charge degrees of freedom, the other degrees of freedom seems to behave like similar in spin liquid material and superconductors. So I think that such a kind of the spin-on Fermi surface instability is one of the conceivable. Yes?
Does that compare? I mean, what about the heat capacity of that?
Yeah, that is a very difficult one, because at low temperatures, the phonon contributions dies, and then electron contribution shows up. However, at high temperatures, maybe around 10 Kelvin, 10 Kelvin is TC is 10 Kelvin. In that case, maybe 99% of the specific heat coming from the phononic part. So it's some anomaly occurs in superconductivity. Is some anomaly occurs, and then, however, yeah. This can be some origin of the some spin of Fermi, but I don't know. I'm not sure. Because the temperature is rather lower, 6 Kelvin. This is the delta C divided by temperature. So the whole specific heat is very huge, and then lattice part is subtracted, and such a broad shoulder results. But in this sense, this shape and then the anomaly associated with the superconducting transition looks similar, yeah, like this. But we cannot compare in detail the two behaviors. But I'm not, yeah.
Is there a measure of how large spin lattice coupling is?
How to measure the spin lattice coupling? I don't know.
I mean, somehow it seems that there's, at least in...
This one? This one?
Yeah, I mean, it seems that this anomaly is showing up pretty prominently there, so...
I'm not sure. I don't know how to extract the information on the spin lattice coupling. But anyway, yeah, this anomaly occurs. It's electronic and the spin and lattice, so there is a coupling between this. But I don't know how to or characterize it quantitatively. But anyway, some coupling is there. Yeah. Okay. The other thermodynamic considerations is possible by watching carefully the phase diagram, and that's all about the Clausius-Clapeyron. If the transition is first order transition, in that case, this is the plane, temperature and pressure, for example, and this is the Clausius-Clapeyron relations. This slope, dt divided by Tp, the derivative, the slope is equal to the difference of the volume across the boundary divided by the difference of the entropy across the boundary. And if the slope is like this, it's a positive. In that case, this is positive, and volume difference is always positive, because under pressure, volume necessarily shrinks. So this VA minus VB is always positive. So this is so if this slope you have the SA minus SB should be positive. So entropy entropy of the A phase is greater than that of B phase. Or if the slope is negative, the reverse situation, opposite situation occurs. In this case, the entropy of A phase is smaller than that of the B phase. Okay, let's take a look at the phase diagrams of the two materials. One is the anti-ferromagnetic Mott insulators. The other one is the spin-liquid Mott insulators. So you see a very contrasting phase boundary, which shows a negative slope in anti-ferromagnetic case and then positive slope in spin-liquid case. So even in the anti-ferromagnetic case, at high temperatures, the slope is positive. So okay, positive slope means that the entropy of the A phase is greater than the B phase. It's a very reasonable because in the spin liquid materials, the spins are very alive. It's vital, though. So the spin entropy is very high compared with the film degenerate metal, film liquid. But in the anti-ferromagnetic case, the slope is reversed. Why? And this is the anti-ferromagnetic ordering temperature here. But even at ordered temperatures, the short-range ordering occurs. This is very clear because around this near-ordered, there is no specific heat anomalies. This means that the short-range order is derived at higher temperatures. So this reverse means that the spin entropy is high at high temperatures because all of the spins are paramagnetic. And however, at low temperatures, short-range orders, the spin entropy is gradually dying and die out and die, and then the entropy of this A phase is smaller than this one, the metallic one. So it's a very, very reasonable. And some of you know the phase diagram of V2O3. It's a very famous Mott transition systems. And in V2O3, the case, in that case, this phase boundary is like this. Yeah. Pressure and temperature. First order temperatures and metal. And this is the insulator, paramagnetic insulators, and like this AF. And this is three-dimensional materials. There is no prominent short-range fluctuations. So once antiferromagnetic orders occurs, the entropy balance is suddenly reversed. This is a three-dimensional case. But in a case very strongly two-dimensional, highly two-dimensional, so at high temperatures, magnetic order like this, but still high temperatures, it's a short-range orders, so like this. This is the explanation of this phase diagram. Okay, and from the phase diagram, we can guess how the entropy dies out at low temperatures. And let me emphasize that in spin liquid materials, the spin entropy is still alive at low temperature. However, please take a look at the low temperature behaviors. This slope is gradually changes in the tangential at low temperatures. So we proceeded to the detailed the experiments to determine the precise phase boundaries. Yeah, it's the same material. So the material is this one, the spin liquid material. The temperature is very low and precisely determined. This is the Mott insulator. It's a spin liquid insulator, and this is metal. and superconductivity occurs below 3 kelvins, and this superconductivity neighbors the spin liquid. Okay, from this boundary, this red curve is a fitting of the boundaries. So from this slope, by using these relations, you can get the entropy difference as a function of temperatures. You see, around 6 or 7 kelvins, the entropy balance is reversed. At higher temperatures, the spin entropy of the spin liquid is higher than the film liquid. However, below these temperatures, the entropy of the spin liquid is smaller than this metallic film liquid. So it may suggest that some less entropy state is stabilized at low temperatures. Okay, so this is an entropy difference, and assuming the entropy in the metallic states like this, the gamma T, and the gamma is inferred from the spin susceptibilities under pressures by using the Wilson ratio of 1. In the metallic state of this family of materials, many materials shows the Wilson ratio of 1 in the metallic state. So the gamma is guessed to be 27 or 28 millijoule in this material. So this is the inferred spin entropy of the spin liquid. Okay, this is this around 5 Kelvin or 6 kelvins. Some rather steep increase occurs. So something happens here. So, but to deduce, to obtain the entropies, we have to know the difference of the volume, delta V. But we don't know delta V. So delta V, V is parameters. And we calculated several, the entropy for several values of V. It's difficult to see. The 1 something, 1, 2, 3, and 10 to the minus 8 something. But if we assume the 3, these values as delta V, in that case, the resultant spin entropy shows a peak. This is unphysical. Even by using the second values, it's a tendency. Entropy tends to form a peak, so unphysical. So I think that this blue curve data well makes sense. So this is the tentatively obtained temperature dependence of the spin entropy of the spin liquid, I think. Yes? This resistivity. Below 3 Kelvin, this is a superconductivity. So we cannot clearly determine the phase boundary because, how to say, some sort of superconductivity occurs, and this is some percolative superconductivity affects this insulating rate, the behavior of the insulating phase. So we cannot clearly determine in below 3 Kelvin. This is experimental restriction. Okay, more interesting data is the evolution of the behavior of the charge degrees of freedom and the spin degrees of freedom. The right-hand side figure shows the evolution and the change of the temperature dependence of resistivity. This is the ambient pressure data is insulating the many decades. Okay, for example, 85 megapascal here, the spin liquid insulator. And along these lines, the resistivity behaves like this. Like this. Very good insulator. Okay, and at this pressure, the anomaly relaxation rate 1 over T1. 1 over T1 proves the spin fluctuations, as I explained yesterday. And 1 over T1 behaves like this, the green symbol. Okay, green symbol like this. Okay, along this line, it's at high temperatures is insulated, but at low temperatures, the system enters into the metallic states. So this corresponds to maybe like this. Yeah. So very huge difference. However, in spin degrees of freedoms, there is no qualitative difference. Okay. For example, if you look at the data above 3 kelvins, there is no qualitative difference. The gradual change. This is a Fermi. Oh, sorry. This is the Collinger relations. Here, metallic state. It's the Collinger relations, and the Collinger level is gradually lifted, and this at lower pressures. Okay, so in particular, in this temperature range, this change is very smooth. This is the paramagnetic state, and then crossover to the ferromagnetic state here. So even in these regions, such a kind of the crossover seems to occur. So this is my tentative opinion. And in charge degrees of freedom, it's a localized and then metal ferromagnetic. But in spin degrees of freedom, maybe ferromagnetic behaviors are always in the phase diagram, I think. So these behaviors is a very unpublished data, and then it's a tentative preliminary data. But I think that this is very possible indication of the existence of the spin-on, ferromagnetic spin-ons in these materials. Very clear contrast between the charge degrees of freedom and spin degrees of freedom.
Just for comparison,
Yes?
I wonder, can you say what you would expect if you were insulator and then?
Yeah. Yeah. I yesterday explained something about that. Spin susceptibility shows the like this. Shows the behavior like this, and T, and spin susceptibilities, and so like this. And this data is well reproduced by the triangular lattice Heisenberg model. And this means that it's at high temperatures, in maybe around this temperature range. At high temperatures, maybe the short-ranged 120 degrees spin configurations are fluctuating. But at low temperatures, and maybe the 120 degrees of ordered state is not stabilized. So some no ordering, so some ferromagnetic state occurs. So maybe there should be some crossover between this high temperature state and the low temperature ferromagnetic state. So this peak, this can be a crossover between these bosonic excitations to the ferromagnetic excitations. This is a guess. Okay, this is the low temperature behaviors, and additionally, the interesting behaviors occurs at high temperatures. This is the phase diagram in these regions. So if you look at the high temperature regions of this phase diagram, yeah, extended up to 100 kelvins, there is a very interesting crossover regions, which is indicated by the color, a range of the colors. And this is the quantum critical behavior. It's shown in these regions. So I'd like to show some results about concerning this finding. Okay. Okay. So what we did is the resistivity behaviors in these regions as functions of temperature and pressures are scaled in a quantum critical manner. Okay, what we did is very simple. Temperature is fixed, for example, here, and then pressure is swept, and resistivity is measured. This measurement is repeated at different temperatures, fixed. Okay, the obtained results is like this. For example, at 25 kelvins, the resistivity is insulating and gradually changes. This is the high temperature data. So there is no first order transition. It's a crossover region. So the change from the insulating state to the metallic film liquid state is smooth. It's very continuous. And okay, and this inflection point is determined to be the crossover point, which is rationalized by some DMFT calculations, which I showed you later. Then all of the experimental data is reduced to have the common inflection point here. So pressure scale is shifted. Then this horizontal scales is horizontal data. The data is scaled in horizontal directions by multiplied by a factor. The factor depends on the temperatures, the different temperatures. So all of the experimental data collapsed into this universal curve. And to obtain this the universal curve, the data at different temperatures has a different correction factors. There's different correction factors follows this scaling factors. In this case, that z nu is 0.6. It's as exponent of the quantum critical scaling. This is a quantum critical scaling. And yes.
Did you scale it with T or T?
No, T. It's a T. No T minus TC. Okay, so if you take the T over T0, T0 is reduced temperatures. This data collapses to the two branches. This is experimental data, not calculation. All of the experimental data collapse to the two branches. This is an insulating branch. This is a metallic branch. And these universal curves have nearly perfect mirror reflections. And this is the very characteristics of the quantum critical behaviors. So this shows the quantum critical characteristics emerges and this in the high temperature region of this Mott transition. And yes, and this is color plot. The color means that the value of the reduced resistance, the normalized resistance. So this colored region is a quantum critical regions. This blue region is a very good insulator. It's a middle region here. Okay. If this rhythm line, the crossover line, is converted to the vertical line, so this phase diagram looks like this one. It's a nearly perfect mirror reflections as expected M quantum critical transport. And this behavior is not specific to the spin liquid materials. This high temperature behaviors is commonly seen in other Mott transition systems. We examined the behaviors for different materials and with having different ground states. These materials and the other materials, these materials is the anti-ferromagnetic insulator and the superconductivity. And these materials shows in the insulating layers, in the insulating phase, in the spin liquid and the metal, no superconductivity. So different set of ground states appears in different materials. However, the scaling is nearly common, nearly the same. And the data is missing here because this is located in the very close to the Mott transition boundary. So we cannot access the negative pressures. So data is missing here. But anyway, all of the materials shows nearly the same quantum critical behaviors. And the Z nu value, the exponent for 3 materials are located around here, 0.5 to 0.7. Okay, this material, the Z nu, 0.61, roughly saying that 0.6 plus minus 0.1. But I'm not sure this difference is that makes sense or not. It is likely that this difference is an experimental error. But anyway, this is a comparison of experimentally determined the Z nu values and some theories. And the continuous mode transition and the DMFT calculations predicts the similar values. Okay. Okay. Let's summarize this part. This is a comparison of the phase diagram of the spin liquid material and then antifilm materials. And the important point is that at high temperatures, the different materials seems to show the very universal behaviors. There is no difference at high temperatures. However, at low temperatures, the detail of the systems is reflected in the behaviors. Namely, the degree of the frustration of the lattice. So spin liquid appears here, antiferromagnetic appears here, but TC is lower in this case, but in less frustrated case, TC is higher, 3 Kelvin and 10 Kelvin. And pseudo gap or preformed Cooper pair appears in this material, but this no. So very different behaviors appears at low energy scale. Reflecting the details of the system. But at high temperatures, yes?
What is the nature of this critical?
Critical, you mean this one?
The critical endpoint.
Yeah, here and here. Yeah. This is the usually expected in the for the phase transitions without similar breaking. And the phase transition without similar breaking should be the first order of crossover, likely gas-liquid transitions. So this critical, imaginable critical endpoint is a very natural consequence.
You notice this, if you measure the critical electrons, same as critical point?
Yeah, that's a good point. It's controversial. It's yes, gas-liquid critical universality. The gas-liquid transition has the same belongs to the same universality group as Eisen. Yeah, but we determined the exponent, but different. But still controversial. Some other groups reported that the critical exponent is exactly the same as the gas-liquid transition. So it's a controversial, yes. Yeah, we determined that this T minus TC, but in this temperature range, the resistivity is scaling. But at high temperatures, the critical TC is in this case 20 or 15 Kelvin. So the data is also scaled if we use T minus TC instead of T. But at low temperature region, the scaling is failed. Rather than T minus TC, the T scales the data. That is our feeling. But we cannot say definitely T minus TC scaling is not ruled out or not. Is not definitely answered. Okay, but this is experimental data. But our experiments were motivated by the theoretical studies conducted by the Brad, Dobrosavljevic, Tarahashi. They similar and calculated the conductivity using the DMFT framework, and this is a well-known phase diagram deduced from the DMFT at first order transition line and critical point here. And in these regions, they calculated the resistivity, and the resistivity follows the quantum critical scaling. That is a suggestion, theoretical suggestion. And later, we examined the behavior in real materials, and we obtained the results which I explained. Okay. And the physics behind this quantum criticality is like this, I think. And the very famous system that shows the quantum critical behavior is the heavy fermion systems. And in this case, the RKKY and the Kondo are competing. And this competition between the two interactions gives a quantum critical behaviors from the Néel ordered and then heavy fermion systems. But in our case, it's very analogous to the Kondo systems. In the Mott systems, the computing energy scales is kinetic energies characterized by the bandwidths and on-site Coulomb interactions. Both energy scales are several thousand Kelvin. Okay, and in Kondo systems, the Kondo and RKKY. And in the Kondo cases, the parameter is a J, the hybridization. But in this case, the bandwidths, the transfer integral, they are closely connected. So, however, in our case, in the Kondo case, it's different from the Kondo case. In our case, the Mott transition is not associated with the similarity breaking. So similarity is perturbed. So as you say, that the first order transition will crossover, and first order transition occurred at low temperatures. However, the first order transition has the very low critical point, end point, 20 kelvins. But computing energy is 5,000 kelvins. Very huge energy scale. So why not quantum critical behaviors even in the first order transition systems? And in reality, indeed, we observed quantum critical behavior in this. So we think that the quantum transition is not a necessary condition for observing the quantum critical behaviors, even when the transition is of first order. This critical endpoint, if the critical endpoint and then computing energy has a very different, the intermediate energy, namely at high energy scales, system can behave like quantum critical system. Okay. Yes?
You were showing data up to about 100 Kelvin.
Yeah?
That's experimental adaptation because.
Are you asking that what about at higher temperatures? Yeah. We measured at high temperatures. So the scaling fails at maybe 120, above 120 kelvins. So I see that at high temperatures, the phonon contribution is huge. So we guess that the fail the scaling is due to some phonon contribution. Anyway, results does not follow the scaling at above 120 Kelvin. Okay. So I'd like to show you the another route to the spin liquid. Frustration of the lattice is very important to obtain, to have a spin liquid or frustrated magnetism. However, disorder plays a very interesting role in generating the spin liquid materials. So I call it the quantum disorder by quench disorder. Okay, again, let me show that the two the NMR data of the two materials. One is anti-ferromagnetic order. Ordering occurs, and the other one is spin liquid. We can convert this material to this material by introducing this soda. Okay, what we did is X-ray radiations, and okay, we irradiated X-ray to these materials, classically ordered state, and like this. And by examining optical measurements, what occurs under the X-ray irradiation is some breakup of some atomic arrangement or chemical bonding in the insulating layers. And this is the optical measurements, namely the infrared spectra of some stretching mode in the insulating layers. So in the insulating layers and the ET molecules. And as the irradiation is increased, the time of the irradiation is increased, this ET molecule does not show any change in the intensity of the absorption of the stretching mode. However, this CN stretching mode, this is the anion, the insulating layers. Yeah. The peak is decreased. This means some leakage or destroy of this chemical bonding. So by X radiations, some disorder occurs in this in insulating layers. However, spin susceptibility does not show any Curie term. If the sample contains some defect, it's a conventional defect, in that case, the magnetic susceptibility should show Curie-like behavior at low temperatures. However, no Curie-like behaviors. Oh, sorry. So this means no orphan spins are there. No imperative spins are there. All of the spins are strongly interacting. No free spins. And disordered. Okay, this is the NMR data. This is the NMR spectra before X-ray irradiations, and after irradiations, NMR spectra shows no change down to 340 millikelvin, 0.3 millikelvin. This is the spectra superposed. All of the spectra nearly the same. So this means before X-ray irradiations, the NMR spectra shows a clear splitting, the magnetic ordering, but this magnetic ordering is completely gone by introducing disorder to the system. It's a very curious and interesting feature. And this is the NMR relaxation rate. Okay. Before irradiations, the 1/T1 shows a sharp peak. This is the clear manifestation of the antiferromagnetic ordering, because at high temperature spins are fluctuating, but when the spins are ordered, in that case the motion of the spins are restricted. So only the spin wave or some kind of restricted only the restricted spin excitation occurs. So this shows NMR relaxation rate shows a very sharp peak around magnetic ordering. But this peak is gone after the X-ray radiations, and the temperature dependence of T1 is proportional to T, the square root of the temperature. This temperature dependence resembles that of the pristine spin liquid. So we think that the spin liquid is generated from the classical magnet by introducing disorder. However, we have to pay attention to the charge degrees of freedom. This is the insulator. However, after the X-ray radiations, the temperature dependence for resistivity is changed from the gapped behavior to the gapless behaviors. And this temperature dependence is very, very weak temperature dependence, still insulating. And this temperature dependence is well reproduced by the variable range hopping. This means that it's insulating, but very, very disordered insulating state. So this state is regarded as a Mott-Anderson insulators. Mott insulator, but a very serious disorder is introduced. In such a case, a gap is collapsed and very disordered Mott-Anderson insulators, where the interaction and disorder plays similar roles in localizing electrons. So why, in such a situation, why spin liquid-like behavior is stabilized? And this is a guess. One point is, okay, maybe spin liquid resides just behind the frustrated antiferromagnetic. is this classical ordered state in copper chlorine material. It's a deformed triangular lattice. Its a ground state is antiferromagnet. However, maybe spin liquid is maybe behind, residing behind the antiferromagnetic ordered state. Maybe that is one conceivable situation. The second one is this is a very interesting to me, interesting suggestions from theoretical point of view. Our guess is a spin liquid is maybe ubiquitous in Mott-Anderson insulators because this is a wave function, cartoon of the wave function. In the Mott-Anderson insulators, the wave function, one-year-like wave function, is very, very deformed. And the spin-spin interaction, very, very complicated, we think. In such a situations, why not spin liquid behaviors? But our observation suggests that in these situations, the charge are frozen in a glassy manner. However, spin can mobile as a mobile spinors. And such a situation, such a suggestion was made in theoretical works by two groups. So I speculate that spin liquid is very ubiquitous in Mott-Anderson localized states. So we are now doing such a kind of experiments in other Mott-Anderson insulators. Okay. Next, doping a spin liquid. Spin liquid we have. Probably we have the spin liquid candidate in organic materials. But organic materials are not good at being doped. The doping is a very effective method in high temperature superconductivity or transition metal oxides because the transition metal oxides easily accommodate alien atoms with different balance. However, organic materials dislike that alien species with different balances. So that is a main reason why the doping in organic materials is not successful. However, there is exceptional materials we have. And that is this one, the copper type materials, the similar structures. However, the different is in the anion species, in the insulating species. Mercury 2.89, bromine 8. It's a non-stoichiometric materials. It's a very, very funny. We synthesize these materials and characterize this content. Always the mercury content is 2.89. So this is not accidental. This has a very good reason because the mercury is a very, very strange element, and in compounds, mercury often forms its own periodicities incommensurate with other hosting lattice. And such a situation occurs. So this the missing content, for example, 0.11, is not a defect. Mercury forms an incommensurate superlattice in the insulating layers. So this 0.11, this missing content serves as whole doping. So 11% whole doped in the Mott insulating layers. And okay, so we have spin liquid insulator and 11% whole doped Mott insulator. And additional interesting point of this material is that T prime over T is unity. So nearly triangularis we have. So we have two nearly triangularis materials. One is confirmed spin liquid to be a spin liquid. And the other one is a doped material. This is the metal. So let's compare the magnetism and the conductivity of the two materials. It's very striking. Okay, this is the scaled susceptibility as a function of temperature, and then J multiplied by the spin susceptibility multiplied by J. And blue symbols are the data susceptibility of the spin liquid insulators. And red symbols is an 11% hole doped spin liquid. Nearly the same. So this means two materials show exactly the same behaviors in spin sector. However, let's take a look at the inset, the resistivities. And the spin liquid materials is insulating, good insulator. However, doped spin liquid shows good metal. And in reality, this metallic behavior is non-film liquid-like, T-linear. Yes. So, in charge sector, the behavior is completely different. It's an insulator and metal. However, in a spin sector, exactly the same, nearly exactly the same. This is the clear manifestation of the spin-charge separation. Okay. So, even in a metallic state, in spin sector, spin behaves like spin liquid. So that's why we say that we have a doped spin liquid. This is very recent data, unpublished. And this is the pressure experiments of the Hall coefficient as a function of pressure. Okay. And yeah, please take a look at the low temperature data, a Hall coefficient, yeah, like this. At the low pressure, the Hall coefficient is very high. This means that it's very small carrier. But at high temperatures, the Hall coefficient is decreasing and very low value at high pressures. There's some crossover occurs around 0.5 GPa. So this is the cartoon. At low pressures, the mobile charge are very small, low density, carrier density is low, but at high temperatures, it's many carriers. So we speculate this is a sort of a Mott transitions. Double occupancy is prohibited and allowed, crudely speaking. So in these high temperature regions, all of the electrons participate in the conduction and then contribute to the filmy surface, a large filmy surface here. But at low pressures, only a small portion of the electrons contribute to the carriers. Probably the doped holes. So it's a holon and other sites are occupied, accommodated by the spinons is here. So in these regions, this spin, maybe the spinon, behave like a spin liquid, as in the spin liquid insulators. And this doped hole is a mobile. It contributes to the conductivity, high conductivity. So in high temperature regions, it's a conventional correlated metal, but in the low temperature region, it's a doped spin liquid, doped Mott insulators. And the temperature dependence is very interesting. This is the exponent, temperature, pressure. At high temperatures, the exponent of resistivity is 2. It's a film liquid. But in these regions, 1, non-film liquid. So this is a non-film liquid. This is a film liquid. Very clear correspondence. Okay, I skip. The time is limited. So one interesting point. This shows superconductivities as a function of pressure. And interestingly, the TC forms a dome, and the maximum occurs around 0.5 GPa. Roughly occurs here, maybe 0.4 or something like this. Around these pressures, TC may be maximized. Okay, this is the resistivity measurements under pressure. And for example, you see the magnetic field and resistivities. At low magnetic field, it's superconducting and resistivity is vanishing. However, magnetic field kills the superconductivity and gradually changing. And the magnetic field is applied perpendicular to the layers. And this material is strongly two-dimensional. So in these situations, namely under the perpendicular magnetic field, the vortex liquid-like states occur. So this intermediate resistivity range, the superconductivity and normal states, kind of normal states, are mixed and fluctuating in the form of the vortex liquid state. And then nearly normal state appears, is recovered at high magnetic field. And this is a color plot of the resistivities. In the low temperature region and the doped spin liquid region, it's a normal state here. And the blue color roughly indicates that the vanishing resistivity. So vanishing resistivity here and normal state. The change from the zero resistivity to the normal state resistivity is gradual, no clear cut, the clear boundaries. But however, if you apply pressure further, for example, at the boundary, this zero resistivity region is extended and normal state here. And at high temperature regions, and in these regions, the conventional highly correlated metal is realized. In this case, the transition from the superconducting state in the normal state is very clear, very sharp. It's a conventional behavior. So in such a case, it's not so straightforward to determine the upper critical field. Upper critical field means characterizes the magnetic field which kills the superconductivity. But we define the critical field in this the resistivity 80% recovered the point. And from the upper critical field, we could determine the coherence length. The coherence length is, roughly speaking, characterizes the scale of the Cooper pairs, roughly speaking. Okay? So please take a look at this one. And this purple curve indicates the rough estimate of the inter-Cooper pair distance. Okay? At high pressures, high pressure regions, we assume that all of the electrons participate in the superconducting state. In these regions, coherence length is much larger than the inter Cooper pair distance. This means that in these regions, Cooper pairs are overlapping, many overlapping in the BCS state, BCS-like state. But in this doped spin liquid regions, coherence length is diminished, and the Cooper pair distance, average distance, is increased and nearly the same. So overlapping is small. So I think that in these materials, as a function pressure, the BCS to BCS crossover occurs. This is a additional interesting aspect of this doped spin liquid or superconductor. Yes?
So can you go to a previous?
Yes. Yeah.
What do you mean by
yeah, it's a very important point. We measure the superconductivity by AC susceptibility measurements. But in these regions, superconductivity is not complete. Maybe at ambient pressure, the fraction of the superconducting volume may be 30% or something like this. But I don't know. I'm not sure about the reason. However, under pressure, the superconducting volume fraction becomes full, 100%. So this inhomogeneity, maybe I think the intrinsic properties, I think. If the system is dirty, such a fractional superconducting volume, incomplete superconducting volume superconductivity is maintained even at high temperatures, but high pressures. But in a case, at high pressures, superconductivity is very clean. So I think in these regions, I'm not sure about the origin of the inhomogeneity.
Is it a hollow, like or is it
but the characterization was made at zero magnetic field. So FFLO appears in the high magnetic field. If you mean FFLO, fluid FFLO?
FFLO like because the mechanism for having doesn't have Something random.
I don't know, but the inhomogeneity is absolutely different from the FFL because the state is the superconductivity is characterized by a very small magnetic field. But so sorry.
But like some sort of
PDW. Is upper critical field. Yeah. So, but yes. So in these inhomogeneous regions, we did not determine the coherence length. We determined the coherence length in the homogeneous regions. Okay. Okay. Maybe remaining 5 minutes or so. So, okay, skipping the superconductivity, but I'd like to show you a different taste of physics in organic materials. Is okay. This one, the optional material, massless Dirac fermions, is related to topological stuff. That is the subject of this lecture. Maybe 10 minutes. Okay, the material is this. Is like this. Again, layered structures, seemingly similar to the copper type materials, but difference is in the implane molecular arrangement. The copper type material has dimeric molecular arrangements. Dimer forms two-dimensional layers. So dimer carries one hole. So effectively half field is realized. But in this case, no dimer, no dimeric. So this means the bond filling is a quarter. And the unit cell contains 4 molecules and A, B, C. A and 2 A molecules are equivalent, but B, C is non-equivalent. And this is a phase diagram. At ambient pressure, this material shows a charge order at 135 kelvins, and under pressure, this charge order temperature is decreased. And then above 12 kilobar, Dirac fermion phase, Dirac phase appears. Okay, I'd like to show you the interaction effects. Okay, this phase diagram suggests the Dirac state is strongly correlated because the charge ordered state is enabling. So I think in this organic materials, you have strongly correlated massless Dirac electrons. And in the remaining time, I'd like to show you 2 experimental indications. One is the anisotropic cone reshaping due to the long-range Coulomb interactions. And the other one is the ferrimagnetic polarizations, very curious behaviors due to the short-range Coulomb interactions. Okay, this is a comparison of the very well-known graphene and this material. And in the graphene, in the L space is a honeycomb lattice, very highly symmetric. And reflecting this symmetry, and even in the K space, the Dirac cone is symmetrical, and Dirac points is located on the very special point of the boundary in the K space. However, in the organic materials, this is bond structure calculations. And unit cell contains 4 molecules, so the bond contains 4, bond structure contains 4 band. And the Fermi level is fixed here because this is a quarter field, 3 quarter field. And you see, this is the expansion of this, the profile of the dispersion around the Fermi level here. So tilted cone, seriously tilted cone, Dirac cone is suggested, predicted. And the ratio of the film velocity is 1 order different. Precisely speaking, 8 times different. Okay, and the transport measurements confirms that the Dirac, massless Dirac fermions are there in these materials. And an interesting point in the mass direct fermions is the effect of the Coulomb interactions. In conventional materials, conventional metals with Fermi surface, in that case, many electrons, so Coulomb interaction is screened. And short-range Coulomb interactions gives a mass renormalization, or Fermi velocity is suppressed and density of states are enhanced. However, in the Dirac fermion states, the electron density is very small or vanishing at low temperatures. So long-range Coulomb interactions is unscreened. So the long-range Coulomb interaction plays a vital role in mass Dirac fermion phase. Okay, the long time ago, because of predicted in such situations that the Fermi velocity is renormalized, and like this, logarithmic renormalization. It means that if the cone is like this, because of predicted, this logarithmic correction means that if the energy scale is diminished, in that case, this Fermi velocity is sharpened. This is logarithmic corrections. Whether this situations occurs or not in real materials is a very important and interesting issues. And in graphene, by transport measurements, this prediction was demonstrated like this. And our first aim to do these experiments is to confirm the Dirac cone reshaping in tilted cone case. And this material the material has a very interesting electronic properties. This is the band structure calculation, the calculated band Dirac cone, and this color is the amplitude of the molecular orbitals of each molecular orbitals in Dirac cone. Now, for example, the B molecule, this molecular orbital contributes to this steepest part of the cones. However, in the gentle part, there is no contributions. So if you know spin susceptibility of the B molecule, you know the spin susceptibility in the steepest part. Interestingly, the C molecule, C orbital, contributes to the Bloch state, to this gentle part. So the reverse opposite situations. But this C molecular orbital does not show sizable, non-sizable contribution to the gentle part. So if we do the site-selective carbon-13 NMR, which probes the electronic state separately at each molecular site, we can know the local spin susceptibility here and here. And anyway, if the Dirac cone is preserved in such a shape, the density of states is like this. Oh no. Okay. At 0 temperatures, it's this density of states fully occupied. But in cavity, at finite temperatures, in cavity, it's a particle excited, and the average density of states contributes to the spin susceptibilities. So the temperature dependence of the spin susceptibility should be linear in these situations. Okay, that is the first point. That is a result, and we successfully probed the local spin susceptibilities at C molecule, A molecule, and this B molecule, And this is the spin susceptibilities and this gentle plot of the cone. And this B site probes the steepest plot. Okay, and A sees the average, an average. So now please neglect this A site. Please take a look at the B and C particularly. And this is the boundary structure calculations. Density of states is a linear. So in such a case, you expect that the linear temperature dependence of the spin susceptibility at each site. But what we observed is a nonlinear behaviors, completely different. And this is the clear manifestations. In real materials, cone is not like this. It's a kind of the sharpening occurs as predicted by Ablikosov. So students perform the renormalization group calculations. This is the tilted wild equations. And isotropic case that is only these terms are there, but this omega 0 and q describes the tilting. And this Vx and Vy is renormalized by long-range Coulomb introductions. And he calculated the one loop and the large N expansion regions. And this is the RG equations. And they obtained the result. This colored curve, red curve, blue curve, and green curve is a result of the renormalization group calculations. Vx and Vy is renormalized like this. It's a gamma over q. Q is a wave vector in the first Brillouin zone. So q is approaching the 0, means that energy is decreasing and decreasing. So the velocity is increasing logarithmically. Yeah? And this cone is a result which fits to the experimental data like this here. So we conclude that this transparent gray cone is the boundary structure calculations. However, in reality, the real cone is like this. So this cone is reshaping due to the long-range Coulomb introductions. But you see, there is a serious, very sizable discrepancy between this renormalization calculations and the experimental data. As for B site, AC is okay. This is a non-negligible difference. What is the origin of this? And my colleague calculated the, okay, before that, let's take a look at the data more closely. Please take a look at the data here. Okay, this data. And this is the experimental data for the B site. And this is the RG calculations, the large difference. RG calculation cannot explain the behaviors. And this is the comparison of the experimental data for A, B, and C sites. A and C sites shows a very normal behavior, but only B site has negative values. It's a negative spin susceptibility. Is very, very curious because this is a paramagnetic state, no magnetic ordered states. It's a paramagnetic state. This means that you are paramagnetic field, and this is a paramagnetic state. So conventionally, all of the spins are on average the moment aligned to the magnetic field. But this experiment suggests that only B side spin aligned in opposite directions. It's very curious. This is a cartoon that shows the experimental data. Applied magnetic field here, the A spin and the C spin here, but only the B spins are differently. This is not ordered. This is field induced. Okay, So such a ferrimagnetic spin coordination, organization induced by magnetic field. And this behavior is completely reproduced by the Hubbard model, mean field calculation of the Hubbard model. So U is increased. Only on the B side, only at the B side, the spin stability is negative, and such a situation occurs. And this is due to the cone is tilted. Okay, and A side and B side shows conventional behavior, but only the B side shows strange behaviors. So this ferrimagnetic spin polarization is due to the short-range Coulomb interactions. So, and organic mass structure electrons with tilted cones, there are two important effects. One is the long-range Coulomb interaction effects and short-range Coulomb interaction effects. That is reasonable because, as I said, the charge carrier is vanishingly small at low temperature, so long-range Coulomb interaction is not screened. And on the other hand, the charge ordered state is neighboring. So short-range Coulomb interactions are equally important with these materials. Okay, 10 minutes over. Okay.
Very quick questions. Okay, no, let's thank.
We'll come back at 2 o'clock for the afternoon lecture.
I'm a little confused. For the material you are showing that has superconductivity,
Yeah.
does that material has the Dirac?
No, different one,
it's
different,
a very
different one.
What is the material component again for
This one, Dirac alpha ET2I3 is a different one.
Oh, is that on the slide?
Yeah.
I can check it again.
Yeah.
And also, what's the?
This
Do
one.
we know whether they're? The tone of the microphone
Oh, yeah.
is still recording.
Yeah. I'm sorry.
Thank you so much.